In this lesson, we are going to introduce the idea of finding volume by shells. And so there are certain situations that it might not be the best method to use a disk or a washer method. We do have another option called the shell method. And so here's the idea behind it, that if we're trying to find a volume of something, and this is our volume, we're rotating around the y-axis. And this is kind of the tendency is something that ends up being rotated around the y-axis. We don't have to put everything in terms of y. We can leave it in terms of x and use this thing called a shell method. The idea is we're taking these rectangles and kind of rotating it around and creating this look to it. And then so what we're going to do is we're going to cut it, kind of unroll it, and lo and behold, we have ourselves a prism. And so to find the prism, it's basically length times width times height. And so what we're going to do for ours is we're going to focus on this piece right here. Like, what is this piece? This dx is our thickness. And then this piece right here says you're finding a lateral area of a cylinder, which is its circumference. So this length, when you had it rolled, was circumference. And so to find a circumference, it's 2 pi r. And then we need basically a width times a height, and then times the depth to it. And so our height is going to be based on these equations. Right, so here's our height. And then when we roll it, we're going to use 2 pi r. Right, so we have this lateral area is really 2 pi r. That's this piece. And then times a height, which is essentially a y value. All right, so that's going to give us the area of this rectangle, and then we got to multiply by thickness to give it volume. Okay, so here, this piece is our area piece, and then our dx is giving it some thickness. All right, so that's kind of the idea that what you're going to see on the majority of these is, so again, just kind of the main idea is we take these cylinders, and we are basically making more and more and more of them, creating a more and more accurate volume going on. And so that's what we got going on. So it turns into an integral. So for example, we have let r be the region bounded by the graph y equals sine x squared. Just to kind of make sure you are aware that that's the x is being squared. And so we are trying to do, sorry, it's bounded by that, the x-axis, and this vertical line. So it says find the volume of the solid generated when r is revolved around the y-axis. So y-axis, typically we would turn things into y. That gets tricky with trig functions, so we can use a shell method to figure this out. And so our shell method is, we are going to do 2 pi r, so circumference, times height, times thickness. So length times width times height, kind of a measurement. All right, so for this, we're going to be rotating it around the y-axis, 2 pi r. This r value is actually going to be our x just kind of plugged in, right? Because that x is that distance, so that would represent an r value. And so let's do our volume. So here's our picture. Here's our sine x squared, right? And that's going from 0 to pi over 2, because that's what we're bounded by, the square root of pi over 2. And so that's our curve. We're going to rotate it around. We're going to have some sort of kind of funnel-ish looking thing that we're sliding down in the middle. So we're going to go from, rather than rotating around the y-axis and shifting everything in terms of y, we're just going to leave everything and just take a different method to it. So we're going to go from 0 to square root of pi over 2, and then it's going to be 2 pi x, right? X is just x. Our y value is this equation, so times sine x squared dx. All right, so we have a u substitution situation because we have a trig, and trig is always a chain rule, and we have an x squared. And so if we let our u equal x squared, and so our du is going to be 2x dx. So that 2x dx I actually have sitting right here in that equation. So let me rewrite it. I'm going to take the pi out. I always take the pi out. So 0 to pi over 2 square rooted. And I would have sine x squared 2x dx. So I'm just rewriting this to kind of make it a little more, hey, that is going to be du. This is going to be u. And so we're going to have pi. And then I'm going to drop my bounds for now. I'll come back when I put things back into terms of x. So that's what I'm doing the antiderivative of. And so let's see. So I'm going to do the antiderivative of sine. So let me kind of figure out where I'm at in my pattern. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is positive sine. So I'm sitting here doing the antiderivative to negative cosine. So I'm going to have a negative, then I'm just going to attach to the pi cosine of u. And then let's negative pi cosine of x squared. And then I'll put my bounds back in. Cosine of x squared. And we're going to be going from 0 to square root of pi over 2. All right, so let's do the math. Let's plug in. We have a negative pi that we're going to be multiplying in here eventually. And we're going to do cosine of this value squared. So cosine of square root of pi over 2 squared minus cosine of 0 squared. All right, so that's going to become cosine of pi over 2. So let me refresh my graph here. There's my cosine graph. That's my cosine of 0. That's my cosine of pi over 2. So I am getting a negative pi. This is going to become 0 minus cosine of 0 squared, just cosine of 0, which is 1. Cosine of 0 is 1. And that's going to be a negative 1 times a negative pi is going to give me an answer of pi. So even though we rotated around the y-axis, I didn't want to adjust all my stuff into terms of y, especially with the trig piece. And so it was easier, a little bit of a nicer method to leave it in terms of x. But if I'm going to do that, I'm going to need to use shells. And so this is my formula that I'm going to need, but I can leave everything in terms of x's.